Hi there. So today I'm going to tell you about our efforts to study the earliest generations of galaxies in the universe using blue waters. And hopefully it'll be good. Anyhow, so galaxies are the building blocks of the universe, and understanding them is the key to understanding all sorts of things, including the properties of dark matter and dark energy and how we got here, trivial things like that. Also, from a physicist's perspective, they're fun because they are extreme and very complex physical systems. And so I want to talk about some of those challenges and also talk about some of the things that we've learned. But before I go on, I should really mention I'm doing this, this is not a solo effort. I'm working with a bunch of people at UCSD, Edinburgh, Georgia Tech. There's probably one or two other places in there too, but those are the people that are contributing the most to this project. And also, before I go on, I want to thank a few people. I'd really like to thank Manisha Gajbay, who's our technical point of contact, the whole Blue Waters team. We've been real pains in your rear ends. I appreciate that, and you've been very, very courteous and helpful. And the National Science Foundation for funding this whole thing. And of course, the Enzo and YT open source codes. So, okay, let's get started. So here is a picture of the Hubble Ultra Deep Field. That's the Hubble Space Telescope right there. This is a composite picture made from mosaicing together a lot of individual images. It's a very tiny field of view. It's like a grain of sand sort of held at arm's length. It's the deepest image of the universe that's ever been taken in visible light. And it looks back in time more than 13 billion years. And this image, virtually everything in this image is a galaxy. Well, not that, but everything else. And so, since light travels at a finite speed, the further you look back, the more distant objects you look at, the further back in time you're looking. And so this is fantastic for an astronomer because what you're doing is you're seeing the whole history of galaxy formation, or 90-odd% of the history of galaxy formation, just in this one image. And so, if we were smart enough, we could just pull it all apart from this, but we're not, so we need other data and simulations and things like that. But there's 10,000 galaxies in here, and one of the takeaways is that galaxies that are further away, that are very distant, look very, very different than close-up galaxies. By the way, also, the faraway galaxies are really hard to see for a variety of reasons. One is that the Hubble Space Telescope's not actually that large of a telescope, but also because the universe is expanding, the light from those galaxies is red-shifting out of the wavelength range that the Hubble Space Telescope can see. But as we look at more distant objects, we see that they start to look very blobby. And we look at the most distant objects, and they just look like tiny little bits of fuzz. And so, and they're red because the light from them has been red-shifted by the expansion of the universe. But these galaxies look quite different than what we see at the present day. They tend to be full of gas. They're forming stars like crazy. They don't look like those beautiful spiral and elliptical galaxies that we like looking at on the Hubble website. They're quite different beasts. So this is the thing that I've been thinking about a lot. It's the James Webb Space Telescope. It's much bigger than the Hubble Space Telescope. It's got a much larger mirror, also better wavelength coverage than Hubble for the kinds of things that we want to do. It'll look at much longer wavelengths, far into the infrared. And it's going to launch in 3 years or so, supposedly in October 2018. And it's going to be perfect for looking at these earliest generations of galaxies. In fact, that's one of its core missions. So we are trying to predict, using blue waters, what this thing is going to see after we launch it. And again, we're trying to understand these first generations of star formation, or of galaxy formation, because the first generations of galaxies set the stage for all later structure formation. So we want to know what their observable properties are, and we also want to know what their environments look like. How do these galaxies interact with the gas around them and the galaxies around them, and how does that affect what they do? So this wouldn't be a Blue Waters talk if I didn't explain why this is a challenging problem. So from a theoretical perspective, there's a few reasons. One is that galaxy formation is physically complex. We have to worry about a ton of different physical phenomena. We have to worry about gravity, hydrodynamics, magnetic fields, radiation transport. We have to worry about the microphysics of gas, so how it cools, how it heats. Sometimes we have to worry about cosmic rays. We have to worry about how stars form and how they feed back energy and metals and mass into the universe. And we have to worry about black holes and how they form and feed back energy into the universe. So it's very complex, and all of these things are happening at once. There's also an issue of dynamical range. In order to simulate a galaxy, you have to simulate its entire environment. You have to simulate a large volume of the universe, where large depends on what exactly it is you're trying to understand. But you also have to be able to simulate all the way down to the regions where stars are forming, give or take. And so that works out to be about 6 orders of magnitude in space, so factor of 1,000,000. And when you work out the time scales, you similarly run into numbers that are 10 to the 5 or 10 to the 6. So you have really large spatial and temporal dynamic range that you need to deal with. And then finally, there's the issue of sampling. Simulating one galaxy alone isn't good enough, because we see individual galaxies as they are at a given point in time, and they evolve very slowly compared to a human lifetime. And so for us to think that we actually understand what's going on, we need to compare populations of simulated galaxies to populations of observed galaxies, and generally lots of different observable quantities, so that we can get some confidence that we're doing things right. So between those 3 things, physical complexity, dynamic range, and needing to sample a large population, this ends up being an incredibly computationally intensive task. And so the outcome is a problem that is truly worthy of a computer like Blue Waters. So we use 2 things to do this. We use Enzo, which is an adaptive mesh refinement code. That's this thing up here. It does all of those physics, does all those different types of physics that I just talked about: dark matter, gravity, hydrodynamics, MHD, microphysics, all that stuff. It's originally an NCSA production. Greg Bryan was the first author of the code, and he wrote it when he was at NCSA. Since then, it's been developed by many people at a wide variety of institutions. I'm one of the lead developers right now. And it uses a technique called adaptive mesh refinement to concentrate computational cost where it's needed the most. And then, of course, we use this analysis tool called YT, which is absolutely crucial to the analysis efforts that we're doing here, both in terms of finding halos and making sense of galaxy star formation histories, and now we're moving into making synthetic observations, so making predictions of what James Webb would actually see, for example. It's very helpful for all of those things. And there's lots and lots of results. I don't mean you to read through all of these, but these simulations are a gold mine. We've invested 140 million core hours, and we've gotten this many papers out so far, and we're probably going to triple this list by the time we're done analyzing the data. It's been really, really great. And so for this talk, I want to focus on 2 different projects, and that is trying to understand the transition from metal-free star formation to metal-rich star formation. That was something that I did with Britton Smith and John Wise. And then also the evolution of large populations of the earliest galaxies. And this was with a group of people at UC San Diego, and in particular Hao Xu, who's a postdoc there who actually did the simulations. And again, these projects wouldn't have been doable without Blue Waters. It has a fast network, lots of memory per node, very fast disk. These are all things that are good for both the simulations and good for doing the data analysis. Okay, so this first one. So we wanted to understand how the universe transitions from metal-free star formation to metal-enriched star formation. And for those of you that are not galaxy formation folks, let me explain that a little bit more. So after the Big Bang, the universe was made up of hydrogen and helium. Okay, first 2 elements in the periodic table. Hydrogen and helium are really lousy for cooling, so in order for gas to cool to form stars, it does so very inefficiently when your universe is just made up of those 2 elements. And so as a result, star formation takes a relatively long time. It cools really efficiently, so the gas is hot. So you tend to get really large stars at the end, or so we believe. It's actually pretty hard to simulate star formation. But then once you add all the other stuff in the periodic table, which, by the way, are created in stars, in nucleosynthesis inside of stars, and then in supernovae dispersed out into the universe, once you create the rest of the stuff on the periodic table, all of a sudden adding carbon and oxygen and nickel and magnesium and all that stuff makes it much easier for gas to cool. And so instead of having stars whose average masses are 10 solar masses or 100 solar masses, you get stars whose, population of stars whose average mass is more like that of our sun. So much, much smaller and behave in a very different way. And so understanding the nature of that transition is really critical to understanding how galaxy formation started. And so there's a lot of words on here, but basically to do this, we decided to simulate a very small region of the universe at extremely high resolution. So much, much lower than a co-moving parsec. with exquisitely high mass resolution, spatial resolution, and lots of physics. And in particular, we're doing this with radiation transport. And that is quite important because these first generations of stars produce a huge amount of radiation. It really affects the dark matter halos that they form in, and really affects what happens with that second generation of stars. And so, also, by the way, really computationally expensive. So, so you really need a good computer to do that.
How are you doing that?
Raycasting. It's using a technique called Moire, so Weisenabel. So, okay, so here's a movie. So I'm just going to talk over the movie while it's going on, and you can all just gaze on this. So Britton Smith did this movie. So what we're looking at is the formation, the first couple 100 million years of the universe. We have the log of the baryon density over here and the temperature over here at the moment. You can see time moving from left to right on this bar down here. That's where the star is going to form. Right now the radiation turned on, so it heated all of that region up. Then the supernova blew up. Here we switched over to metals, but you can see an expanding blast wave out there if you look closely. And this first halo, this first star to form, is actually not near any other dark matter halos. And so this POP3 star produces this big cloud of metals, but it's got nobody to play with, so nothing happens. And so then there's another neighboring halo where another POP3 star forms. We can see its H2 region, and we can see the supernova explosion from this. And you can see this huge cloud of metals just getting blasted out into the intergalactic medium. And then this cloud of metals is washing over this neighboring halo. And we can watch this happen in sort of, well, relatively slow motion, as this big cloud of metals washes over this neighboring halo and mixes into the halo. Because remember, we're trying to study the formation of the first metal-enriched stars. And so now we're zooming in, pay attention to what these numbers say, and we're just trying to see what's going on in this dense collapse, this dense little region right at the center of the halo. And we're zooming in by several orders of magnitude at this point. So from much larger than the size of the halo down to approximately the size of the solar system. So that's, 8, 7 orders of magnitude, something like that. It's a lot. And so, yes, now we're getting down to solar system scales, and we have this cloud of gas that's forming those first metal-enriched stars. And one of the things that you can see is that this cloud of gas has all of these filaments all over the place. It's really highly turbulent. And so all of the redder parts are the denser regions. Over here we're looking at temperature, and the denser parts also happen to be colder. And there's lots of fragmentation. So here is a little protostellar cloud, and here are several protostellar clouds over here. There's maybe one that's forming right here, one that's forming right there. And so what we see when we get that first little bit of metal in the universe, it causes quite a difference between from a metal-free stellar population. And so one of the things that we can do, we can characterize the metallicity and see that as you collapse, this is the log of the radius of this halo. As you get towards the center, this is metallicity on the y-axis, you go from having all sorts of, tons of dispersion in the amount of metallicity in the gas down to pretty well mixed, and that's just because the turbulent timescales, the mixing timescales are all really short at the center of these, because we're just dealing with transonic turbulence that does a pretty good job of mixing everything together. So the next thing I want to do is tell you about the evolution of the earliest galaxies. And so this is part of the same project, but looking at a much larger physical scale. And so what we're trying to do with this is understand how populations of those earliest galaxies form. And so to do this, we have to pick a much larger simulation volume. And this is doing high resolution, so sort of 20 co-moving parsecs, so about 1 proper parsec at the redshifts we care about. Lots of galaxies, we have thousands of halos, and we're doing radiation transport and things like that in this as well. So 100 million CPU hours later. But basically, the way that we did this was take this big cosmological volume, pick 3 regions out of the volume that we thought would be interesting to simulate. One is what we call the rare peak, which will be a galaxy cluster, this big agglomeration of galaxies at the present day. One that we're calling the normal region, which is going to be a local group, something like the Milky Way Andromeda system at the present day. And then the void region, which is going to be nothing exciting at all at the present day, basically empty. And so we took each one of these, and we just ran it forward in time till we ran out of computer time, quite frankly. And then we stopped, because no computer time. And so analyzed everything. And so first I want to show you what's in that rare peak region. So this is zooming into that simulation. by quite a bit. You can get a sense of what the axes are doing, but it's density on the left, temperature on the right, and this is just sort of panning around so you can see all of the galaxies, all of the ionized regions around the galaxy. So the star formation produces ionizing radiation, and you can see all sorts of stuff all over the place. And what's cool about this is there's something like 1,000 galaxies in this region about 200 million years after the Big Bang. Some of them are pretty massive. They're around 1 billion solar masses, so it's massive by the standards of the epoch. But there's also lots of POP3 star formation going on, so this primordial star formation going on, and the universe isn't really ionized yet. So there's a lot going on. All these galaxies are interacting only with their closest neighbors. The radiation can't go that far. And so it's a very exciting environment to be looking at because there's all sorts of things going on at once. And so one of the things that we find, let's see, okay. One of the things that we find is that when we look at the POP3 stars and we ask, well, POP3 stars are really massive. They end up in metal-enriched halos, halos where there's metal-enriched star formation going on because everything merges really, really fast. And stars tend to form in binaries. And so if you get a really massive star that explodes and then makes a big black hole sitting next to another really massive star, then you can get something cool called an X-ray binary, where it's producing huge amounts of X-ray radiation and does all sorts of stuff to its environment. And so one of the things that we tried to do is see what are the fraction of halos that have POP3 stars in them. Even if they're metal enriched, they might still have POP3 stars from previous generations of structure. And then what's the number of these POP3 stars or relics per halo? And we see basically everything on the large mass side has POP3 stars or their remnants in them. And then once we get to the really heavy side, you have lots and lots of POP3 stars per halo. And some of them, particularly in sort of this mass range of 10 million to 100 million solar masses, have stars that are still active at the time we stop the simulation. And so those might form these X-ray binaries. Another thing we did was look at the luminosity of all of these galaxies. So there's, very few bright galaxies and lots of dim galaxies. And we were trying to understand how many really dim galaxies are there relative to the really bright galaxies. This is one of the key observational things that people try to understand. And one of the things that we found is the observations at these really early times predict that you have this really steep luminosity function. So this, of course, is astronomer speak. So luminosity, as you go to more negative numbers, it means brighter galaxies. I'm sorry, it's just how it is. And so you have very few of these really bright galaxies and many, many of these low luminosity galaxies. And so what we found was that the observations, if you took the later time observations and predicted what it would look like earlier, you should have huge numbers of these low luminosity galaxies. What we find is you don't. They actually quench themselves. And so the luminosity function tips over, and you have about, sort of for each bin, you have about the same number of galaxies. And then here's our void region, our normal region, our rare peak region. And they're very, very different in terms of the total number of galaxies at the same epoch. And so that's very important because if you point the James Webb Space Telescope at these different regions, and we don't have a lot of control over, we don't really know when we look out at that far away what exactly we're going to be looking at. Sometimes you're going to see this, sometimes you're going to see this. So you need to understand how probable it is that you're going to see one of these relative to the other ones. And also we can understand how the evolution of this occurs over time. So this is in the normal region. We can see how at redshift of 18, which is about 100 million years after the Big Bang, you have some galaxies, and then over time it just grows and grows. You get more of them in an absolute sense and brighter galaxies, but always it's flat. And the reason why is that these galaxies, as they form, they quench their neighbors. They actually keep their neighboring halos from forming stars. And so where there should in principle be lots and lots of these halos where stars formation is occurring, the radiation from the neighboring halos just stops that from happening. It's very, very exciting. So let's see. I think that's it for the simulations. So let me just mention, the NSF has invested a lot of time and money in what we're doing here. And we have decided, so myself and my colleagues have decided that we really want other people to take advantage of the work that we've done. And so we want to make our data, our simulation data, a community resource. And so we are making all of this data available through the National Data Service and NDS Labs, working with people at NCSA. And we hope that they're very rich data sets, and people will come up with cool things to do with them that we never would think of. And so hopefully they'll be a community resource for many years to come. So some takeaways. I'll be quick. So first off, modeling galaxy formation is really physically complex, requires a very high dynamic range and a big sample size, so it's very challenging. The transition between POP3, primordial, and metal-enriched star formation is very complex. So I showed you one particular scenario, but there's a lot of ways that it can happen. The outcome is really strongly affected by the presence of dust. I didn't get to talk about that because I put too many slides in here. One thing that we found out was that many POP3 stellar remnants, so black holes, even stars, wind up in each of these massive halos at high redshift. And so you can get X-ray binaries. These could also be the progenitors for supermassive black holes. One of the things that we want to do is investigate how those black holes grow in our simulations by post-processing the data. We also found that the star formation in these little galaxies is pretty inefficient, and they suppress often galaxies that are forming stars very vigorously, suppress the star formation in neighboring galaxies. And so what that causes is a turnover in the luminosity function, which is not at all what we expected. And also, just to reemphasize, this work, particularly the populations of galaxies stuff, would have been completely undoable without a machine like Blue Waters. In particular, there's a lot of memory on the machine, the internet connect is good, and the I/O is really, really good. And all of those things are crucial to being able to not just run the simulation, but analyze the simulation. Thank you very much.